Evaluate the integral from 0 to e cubed of the natural log of x dx. Well, once again, this is a integral that doesn't seem to be improper, but in fact it is. This time, though, it's improper because of the fact that natural log of x is undefined at x equals 0. Think of the graph of natural log of x. It goes to negative infinity as x goes towards 0. It's not even defined on the left-hand side of 0. On the right-hand side of 0, it shoots down to negative infinity. And so this is an improper integral because of that. And so we will address that by introducing a limit. We'll approach 0 from the right-hand side with the variable t. This will allow us to perform the integral, and then we can evaluate the limit. But this is not an easy integral. What function has natural log of x as its derivative? It's not an easy question to answer. So to perform the integration, we're going to have to use integration by parts. Usually with integration by parts, you have a couple functions that are multiplied by each other, and usually it stands out which one you're going to let u equal, which one you're going to let dv equal. But in this case, though, it doesn't even jump out at you that it's integration by parts. But when you let u be the natural log of x, the only thing that's left for dv to be is dx. You take the derivative of u, which will give you 1 over x dx. You take the integral of dv, which will give you just x. You know, it's like integrating 1. The antiderivative of 1 is x. So we put these together in the formula for integration by parts, which is uv minus the integral of v du. So our integral then becomes x log x minus the integral of x times 1 over x. And then, you know, the x's just cancel out. And the integral of 1 is just another x. So it turns out that what we get is x log x minus x. That is the antiderivative of the natural log of x. If you were to take this guy's derivative, what you'll end up with is natural log of x. So we've overcome the hurdle of integration. Now let's go back into our problem, use the fundamental theorem of calculus, and then let's take a closer look at what's going to happen with the limit. So we know that the antiderivative is x log x minus x. We have to use the upper limit of e cubed, plug that in, the lower limit of t, and plug that in, and we have to allow t to approach 0 from the right-hand side. So we replace all the x's with e cubes, replace all the x's with t's, and we could, before we perform the limit, what we can do is simplify with the e cubes. The natural log of e cubed, you know, the property of logs that allows you to take the power of the interior. If the interior of a log is raised to a power, you can bring that power down in front. And so if we have the natural log of e cubed, then that is 3 times the natural log of e, and the natural log of e is just a 1, so that ends up as a 3. Okay, well that's 3 times e cubed minus an e cubed. So then together that's 2e cubed. And what you can do is, since that's not part of the limit, there's no t's involved there, you can actually pull it out. I'm taking the limit of a sum, which is the sum of the limits, or limit of a difference, which is the difference of the limits, but since it has no t, then it really doesn't involve the limit. Let me just put the limit on the part that it really involves, and I can address the limit there, but don't forget about the fact that the 2e cubed is part of it. Part of your solution, that is. So now let's go to the next slide and take a good look at this limit. This is not an easy limit. Let's perform the limit. We have t log t minus t. And we're trying to understand what happens as t approaches 0. The minus t part we don't have to worry about. Okay, that goes to 0. So let's focus on this other part. T log t as t goes to 0. Well, one part of it is headed towards 0. But the other part of it, though, is headed towards negative infinity. I put quotations around it, I can't treat these like, I can't write this. This isn't an expression that I'm allowed to write. And so I put quotations around it. What it actually is an indeterminate form. It could be 0. It could be infinite. It could be some number in between. We just don't know. It's indeterminate. And what we need is to employ L'Hopital's rule. But L'Hopital's rule is only used when you have infinity over infinity or 0 over 0. Both involve a fraction. We don't have a fraction. So we need to create one. Well, if you have a product and you want a fraction, you can quickly get a fraction by doing the following. If you have f over g, if you have f times g, if you have f times g and you want to create a fraction, what you can do is take the reciprocal of one of them. And so that's what we're going to do. We're going to take the reciprocal of one of these guys. Pick one of the terms, and instead of multiplying by it, we're going to divide by it. It's reciprocal. Okay, so the easier one to deal with is the t. We'll divide by the reciprocal of t, and we would not have changed the problem at all. That still is t log t. But now what this creates for us is a fraction. We know the numerator already is going to negative infinity, and as we look and think about what happens as we approach 0, 1 divided by a very, very small number becomes a very big number. So both of these are approaching infinity. One's going towards negative infinity actually, but still quotations around it. This is another indeterminate form, and we can use L'Hopital's rule on it, though it's L'Hopital ready. We can take the derivative of the numerator, 1 over t, the derivative of the denominator, negative 1 over t squared, and do that limit instead. It's called L'Hopital's rule that allows you to do that. So we employ it at that step. Now we consider simplifying before we go further. We're looking at 1 over t, but that's divided by negative 1 over t squared. Let's multiply by the reciprocal. What this does is allows you to cancel this t with one of these two t's that are here, and now we're just looking at simply the function negative t as t goes to 0, and that's going to go to 0. So we go through all this to prove that the limit is 0. It's very necessary. It employs L'Hopital's rule. There's no other way to say it. We can't guess and be sure about it. We have to employ L'Hopital's rule. And then when we go back to the original problem, we see that this part here is going to be 0. So our final answer is that 2e cubed that we got from before.